Good morning, good afternoon, and good evening. My name is Pierre Simonian, and a key takeaway over the past few lectures is primary and secondary bonds. I'll be first talking about the primary bonds, which starts off with covalent bonds, or atoms that bond through the sharing between nearby electrons. They occur between nonmetallic atoms and between elemental solids on the right side of the periodic table. They can create up to 4 covalent bonds per atom. Depending on the arrangement/number of electrons, properties can range from being strong or weak and brittle or ductile. However, most tend to act as insulators or semiconductors. In regards to ionic bonds, these occur when a cation metal and an anion nonmetal transfer electrons between each other. Atoms are both densely packed and non-directional, meaning that they depend on charge rather than the orientation, like covalent bonds do. Properties include being hard and brittle, having a high electric and thermal insulation, having a low chemical reactivity, and a high melting point. In metallic bonds, metals or metal alloys are made up of a sea of free-floating valence electrons, with the positively charged nuclei spaced apart within it, forming these ion cores. Through electrostatic shielding, the free electrons can protect the ion cores from repulsive electrostatic forces. Properties include good heat/electric conductivity and high ductility, due to that sea of electrons. Now, in some materials, such as ceramics or polymers, they contain a mixture of both bonds. The most common mixed bonds are ionic covalent bonds. This equation here determines the prevalence of these ionic bonds. The higher the percentage, the higher the amount of ionic bonds. The lower the percentage, on the other hand, the higher prevalence there are of covalent bonds. Now, the higher percentage leads to a higher stability, meaning a higher melting and boiling temperature. Although they're not conductive at all in their solid form, materials at high percentages are conductive only when dissolved or molten. And in regards to solubility, materials with high percentages are more likely to dissolve polar solvents, and low percentages are more soluble in nonpolar solvents. Like dissolves like, covalent dissolves covalent, and ionic dissolves ionic. In regards to secondary bonding, there are 2 main groups: weaker attraction forces such as the van der Waals and hydrogen bonds. Now, these van der Waals or physical bonds are the weak attractions that occur through both temporary or London dispersion forces and permanent dipole-dipole forces. Hydrogen bonding, on the other hand, is slightly stronger, and it occurs whenever hydrogen bonds with either nitrogen, oxygen, or fluorine. Now, I decided to talk about this takeaway because I think that materials and the bonds that make them up are really important, because after all, it's through those bonds that the properties of these materials can really shine. In the context of this scenario, over the summer I worked at a NSF-funded research institution in which I dissolved MCC or microcrystalline cellulose in ionic liquids such as ammium chloride, which you can see here. You can see here this top image consists of beta-1,4-glycosidic sheets that make up cellulose. And once this ammium chloride is added in, you can see that it breaks apart the hydrogen bonds and it replaces it with these ion-dipole interactions. My name is Pierre Simonian, and thank you for watching.